Welcome to our next topic. Chapter 7 is Direct and Indirect Continuous Pop-PK/PD Models. This is one of the later lectures in the MI210 series. We're going to move through this as a lecture today, and we'll finish with our last topic as a lecture on Friday's 1-hour session. And that will wrap up all of the lectures for this course. A couple of course announcements beforehand. Let me just quickly get to the course site. So in addition to the lectures this week, we're going to issue the final exam. Hopefully that'll be out tomorrow. You'll have plenty of time to get that done. We've extended the deadline to July 26th. But please complete it as soon as you can. Don't let it wait until the last minute, because we will be shutting down the site at the end of July. For those of you who are doing the course project for credit, that project is due on July 26th. I posted last week some details on what I'd like you to include in the posting. The details are also at the end of your course notes. If you have any questions, just contact me. But that's something that should be underway by now, and like I said, you do have through the end of July. Okay. I'm going to turn off the poll here. Just wait another second or two to see if everybody's had a chance to respond. Looks like in our small group who's online today, out of our 10 individuals online, we've had 88% voting. And the breakdown is about 1/3, well, not quite 1/3, 29% say no, it wouldn't be useful. They've already got a local NONMEM install. And the rest of the class, for one reason or another, say it would be useful to have this available. So please contact me if that's something that would be of interest, and we'll see how we can make that available to you. Okay, I'm going to turn off the poll. And we'll switch over to the lecture now. Okay, I've also increased the volume just in case that wasn't loud enough. Chapter 7, Direct and Indirect Pop-PK/PD Models. So we'll talk about a variety of background issues here. Why do we model PK/PD? What are the design and data issues that need to be followed? Some basic models, and then we'll get into the details of how to implement pharmacodynamic models, linked PK/PD models, direct, effect, time-dependent, as well as indirect response models. So lots of different models to discuss today, and we'll have examples of each. Okay. PK/PD models are useful, of course, because they're all headed towards this goal that we have to understand that entire relationship between dose, concentration, and response. Explaining the variability between in the response, not only the PK response, but now we're talking about biomarkers or clinical outcomes. And of course, they provide a framework for clinical trial simulations, which are almost always based on some sort of response endpoint. In addition, there's a regulatory reason for doing exposure response work, and that's that these analyses provide support for clinical efficacy and also demonstrate sensitivity of clinical trials. In fact, the exposure response guidance addresses the issue of a supportive efficacy finding demonstrated through exposure response rather than a second confirmatory clinical trial. One of the key concepts here in the design for PKPD studies is that we want to attain a concentration response range within each individual if possible. Let me just pause a minute here. Sorry, I had double-clicked. Hopefully you're all seeing the screen now. So one of the key points here about concentration response is that we want the range to be observed within subject. So for PKPD models, we can do that by having repeated measures within subject. That's useful for biomarkers, for continuous data, and so on. For clinical outcomes that are sometimes a single landmark outcome, like survival, for example, that's a difficult thing to do. But if there are other endpoints that are rating scales or assessment scores, or even some physiologic measurements such as blood pressure, you can take repeated measures, and you can design studies to allow for a range of concentrations and responses within each subject. When we're modeling, the other nice thing is that we don't have to worry about matching concentrations and responses in time. We can use the PK model to predict concentrations at those time points where we don't have a matching concentration response observation. So you can have maybe less frequent sampling of the pharmacodynamic response as long as we have a predictive PK model. Sparse sampling is possible, but again, remember we want to have multiple concentration response data points per subject. And it's always useful to aim for a variety of scenarios in exposure response. So single dose, multiple dosing, rising concentrations and falling concentration, maybe even different rates of rise, ranges of doses. And this depends upon the particular physiology, pathophysiology, and pharmacology that we're talking about. But it's never a bad thing to have observed more than one set of conditions for the exposure response experiment. And several publications on this topic, including some classic work by John Urquhart and others. So when we talk about pharmacodynamic models, usually we're talking about that part of the model that just relates concentration to response. And so we're not talking about any particular link here. We're just saying that if we have a response E, it's driven by some measure of concentration, and that could be concentration in plasma, concentration in a particular target tissue, and so on. We'll just use it generically now as a concentration. Here's an example, although I've got a typo here. Sorry about that. This sigmoid Emax model, which is effect is equal to some E0 plus some maximum effect times C to the power n and divided by EC50. This should also be raised to the power n. I'll correct that and repost. Plus concentration to the power m. That power term is known as the Hill coefficient. It was described by Hill when he was studying the cooperative binding of oxygen to hemoglobin, but it also stands as a very practical, empirical way to impose a slightly more sigmoidal shape to a concentration response relationship. When that Hill coefficient is at its null value, which is 1, this collapses to a simple Emax model where there is no cooperativity of binding or no sigmoidicity. It's just a standard Emax. We can have a truncated sigmoid Emax where it's now just sloped to a power, also known as a power model. A linear model where we just have E0 and slope, and then we can have a log linear model as well. So there's a variety of different ways to parameterize these relationships. These are just a few. Most of these are all derived from receptor occupancy theory, or the law of mass action, and one way or another, they have a link back to those basic principles of equilibrium binding, and so on. But what we're often doing in these applied PK/PD models is using these mathematical expressions not so much as a representation of physiology, but more as an empirical relationship of the empirical description of the shape of the relationship between concentration and response. So we've seen this already in the class. Here's a simple $pred implementation of a concentration effect relationship. Here we have concentration observed in the data set, and dV is the observed pharmacodynamic response. The key here, again, is remember to define our parameters, Emax and EC50, in terms of a fixed and random effect. And then we define the description of the model. The model for effect here is equal to the Emax times concentration from the data set divided by EC50 plus concentration. And then our residual error is an additive one where the observed data Y is equal to the prediction F plus a residual epsilon. This is a straight concentration response relationship. There's no PK model involved at all. We have observed concentrations only. This is about as simple as you can get. You could get maybe a bit simpler by just using a linear model here, but this is about as simple as you get for a concentration response model in NONMEM or any other tool. What we're most interested, though, in talking about in this topic today is linking PK and PD models. So this is where we have models for the PK and we have models for the PD, and we want to link those together. First, I'll pause for a question. Yeah, there's a question about these Emax, the model equations here. The slope term is really just a shortcut or truncation of the Emax model. If you take Emax divided by EC50, that ratio, when concentrations are very much smaller than EC50, that's approximately a linear constant. And so what we're saying here is that if our concentrations are lower than EC50, we're most likely only going to be able to estimate the slope parameter, which is a slope of in this case, a power model or a linear or log linear model. SLP is equal to slope. Emax and EC50 should be identifiable if you have enough of a range of data such that the concentrations well exceed the EC50 and approach responses near 90% of Emax. But oftentimes we don't have that luxury in the data, and we have to use a more empirical estimate, maybe the ratio of Emax and EC50, which is the slope. Okay. So getting back to link models, we have direct links, we have effect compartments, time-dependent models, indirect pharmacodynamic response models. All of these are ways to link models together, and there are a variety more, even some more mechanistic type models. Remember that these types of models can be used to model continuous endpoints or categorical endpoints. One of the topics that comes up is whether or not to use the model predicted or the observed pharmacokinetic observations in modeling PK/PD. And you can make arguments for either case. Here are some of the key points. If we have a PK model, we can make predictions of concentrations at all observation times. And so there's no need to match pairs. That's a useful way to take advantage of all of the pharmacodynamic data. We don't have to censor out data just because there's not a corresponding PK observation. That's only possible if you use a model predicted concentration. Another thing to think about is that the PK model makes a prediction that is devoid of the residual noise. And if you recall back to any classes you may have had on regression models, the predictive variable is always supposed to be known without error or with much less error than the dependent variable. And when we're modeling concentration response, the predictor variable is concentration, and the pharmacodynamic endpoint is the dependent variable. Well, if we use observed data, and the observed data are very noisy, lots of residual noise, it can lead to problems sometimes in interpreting that relationship, because the more noise there is in the predictor variable, the more blunted, or the less obvious the exposure-response relationship will be. So this is another reason why you might want to use a PK model if it describes the data well, because a PK model makes a prediction of the concentration minus the residual error. So it's a more precise predictor. The other nice part about building the PK model is that we can easily extend that to more complex models if we need an effect compartment, an indirect response, and so on. And of course, PK and PD predictions are dependent upon the accuracy of the model. So if we use model predicted, we've got to make sure that the model is adequate to do so. In general, if you have the model in place, there's a good reason to go ahead and use the model predicted concentrations to drive the PK-PD relationship. Now, if you're going to do that, what should you use? What kind of predictions should you use? Well, we could use the individual predicted concentrations. And sometimes when we have a very, let's say, a complex PK system or limited time frame, we might want to go directly to predicting individual concentrations from a stable base model rather than building all of the covariates. If that base model is unbiased, the individual predictions are not likely to change very much from the base model to a full covariate model. Because remember, these individual predictions include the conditional estimates of the random effects, eta. And those etas will usually accommodate whatever they need to fit the data well. And so it's useful to take this approach when you're making predictions for the current data set only, when you're not really trying to understand PK variability, and of course when your individual prediction provides a good fit to the data. The next topic is a discussion about whether or not to model PK and PD in a simultaneous or sequential manner. And there's some different ways to do this. I'll describe two sequential fits. Sequential fit 1 is when we first model the PK and fixed the parameters to the final individual estimates. So we've done some sort of conditional estimation on the PK side. And then we model pharmacodynamics conditioned on the fixed individual PK parameters, including only the PD data. So all of the PK modeling is done in a prior step, and we capture those individual estimates. Sequential fit 2 is similar, but you model the PK first, but we fix the PK parameters to the final population estimates. And then we can model PK-PD given the fixed population PK parameters, including both the PK and PD data. So this is different now. This doesn't necessarily require conditional estimation for the PK parameters. It does require a population level estimation. And now our PK-PD fit is only conditioned at the population level. We can model the PK-PD relationship at the individual level as a simultaneous component. And then of course there's a full simultaneous fit where we start with initial estimates from a sequential fit, maybe sequential fit 2, and then we allow all the parameters to be estimated simultaneously. And that's been called the gold standard, but I'd be careful to name it the gold standard if you're not using conditional estimation. This is only the gold standard if you're running conditional estimation, such as FOCE, Laplacian, etc. And that's because we want the individual PK predictions to propagate to the PD model. So the sequential fit 2 saves some time. Usually provides pretty good answers if you're using conditional estimation. Sequential fit 1 is less computationally intense and gives us good results if the individual parameters are estimated accurately. Sequential fit 1 would be the preferred choice if it's not practical or possible to run conditional estimation in sequential fit 2 or conditional estimation in the simultaneous fit. So in those cases, let's say you have a really complex PK model, the runtimes are really long, convergence is difficult with conditional estimation, and you've got to run it with FO. When you try to pull it with PD, there's no way it's going to run together. So you run it with FO, and then you generate individual estimates using the post hoc step. If you're stuck in that situation, that's where sequential fit 1 is more useful, because then you can take those individual estimates from the post hoc step, feed them into the PK/PD model, and you're at least maintaining the conditional estimation on the PK side. So that's the one case where sequential fit 1 is a clear advantage. It's when full conditional estimation is not possible on sequential fit 2 or the simultaneous fit. I'll show you how to do each one. So in NONMEM, we can have some simple ways to link these together. There's direct links through the error block. We can build compartmental structures to allow us to build in tolerance or effect compartments, or even differential equations to specify indirect pharmacodynamic responses. Let's start with direct PK/PD. This diagram illustrates we have a one compartment PK model with a first order input from a depot. Effect is some function of concentration in compartment 2. And we're going to develop a direct linked model then. The E is directly related, or effect is directly related to concentration. Well, we're going to look at the code in a minute, but let's take a look at the data set. Here's a little snippet of the data set. First individual, you see it multiple time points. A dose is given at time 0. There's a dependent variable column and a type column. Now this is different than what we've done in PK, because in PK we've only had one type of dependent variable. But now we have a type 1 and 0, where 1 is PK and 0 is PD. This is also known as an indicator variable. And you'll see the first observation is 15. That's type 1. That's a PK observation. The next observation at time 2 is a value of 95, but that's a PD observation. At time 4, there's a PK observation. At time 6, there's a PK observation. At time 7, there's a PD observation. So you see here, we don't necessarily have to have matched times, but we do need to record the timing of the PK or PD observation accurately. The type indicator here will be implemented when we link the PK/PD in the model. For now, it's just useful to help us identify which record is PK and which is PD. So that's the data structure. There's one DV column, but the value type changes depending upon the type indicator. And you continue with the second individual and so on in the same way. We could also do this sort of sequential 1 fit here, where we have the individualized PK sequential fit, where we've already done the PK modeling. And the PK modeling has been done with some sort of conditional estimation, so we're able to obtain conditional estimates of all of the PK parameters for each subject. Those parameters are then fed back into the model through the data set. So here we have CLI and VI, so that's the individual specific clearance, the individual specific volume for subject 1. Subject 2 has a different clearance and a different volume. Okay. These are captured from the first PK run. So now our model is simply including pharmacodynamic data. We're not modeling the PK again. We've got the individual estimates capturing that information. We dose to the system model just as if we were running PK, but the individual PK parameters are fixed to reflect the individual estimates. And that's also done through the model code, where the pharmacodynamic observations now are the only ones listed in the DV column. Okay, so that's how, for a direct model, we can do a simultaneous PK/PD data structure, or a sequential, as in sequential fit 1 for PK/PD. Let's look now at the error block. and I'll pull up the full control stream in just a minute. But the error block here is very useful. As remember, we're probably dealing with a pred-PP subroutine. So we have a model prediction that's available to us in the error block. Remember, the model prediction is F, right? And we can also define parameters in the error block. So here we're going to define Emax and EC50 as a fixed effect with a random effect. These could be defined up in $pk as well. Concentration is defined as the model prediction with some proportional error, error 1. An effect is defined according to an Emax model. Now notice that instead of using concentration in this equation, we're using the variable F. F has a special meaning in NONMEM in the error block. F is the prediction for whatever compartment is identified in the data set. So if we have a direct model and the compartment is 2 here, the plasma compartment, F would be the prediction of concentration in that central compartment. So Emax times concentration divided by EC50 plus concentration. That's your typical Emax model. And then you see we'll have another residual error, error 2, for the effect data. And this is something we typically do anytime you have a multivariate response endpoint, a multivariate dependent variable. You probably want to allow each one of those variable types to have a separate residual variance structure. It could be because there's a different assay involved, different measurement noise, different process noise, but we want to allow that flexibility. So that's why for concentration we have a proportional error using the error 1 as the residual random effect, and for effect we have error 2 in an additive form as a residual random effect. So we can make these predictions at every data record. We can make a concentration prediction, we can make an effect prediction. But when it comes down to comparing to the data, we need to be able to link concentration predictions to concentration observations and response predictions with response observations. So here's how you do that. Remember, y is equal to our observed data. And on the right-hand side, we have two types of predictions. We have a concentration prediction, and we have an effect prediction. Now, it's not that we're saying that the observed data is the sum of these two. We're using an additive relationship here, but that's because each one of these is going to cancel out or achieve a null value of 0 when it's not that type of an observation. So let's run it through for an example. When type is 1, concentration times 1 equals the concentration, plus effect times 1 minus 1, so it's effect times 0. So when type is 1, we have a concentration prediction, and the second term drops out. When type is 0, this term here, concentration times type, drops out, and we end up with an effect prediction. So this is how we can use that indicator variable to switch from a concentration type to an effect type prediction. Let's take a look at the control stream. And I have those in the file browser for you. Sorry about that. So direct PKPD. All of these are posted up on the course site. We have, in this case, PK is 0 and PD is 1. The user has to keep that straight. There's no particular assignment in NONMEM. These variables, these type variables, don't mean anything to NONMEM. We're going to have a combined data set. We're going to do sequential fit. There's PK model, which is, oops, sorry about that. PK model, which is set as you would typically do. Ka, clearance and volume. Then we have an error block, and this is where we're defining the pharmacodynamic model. We have Emax, EC50, plus an E0, an intercept term. All of these have fixed effects and random effects associated with them. We write out the effect prediction. The effect is E0 plus this Emax model with a residual error. Concentration is related to the model predicted concentration here, just as if we had run a PK model. And then y takes on different values depending upon the variable type. Remember, type is flipped this time, type 0 is PK, type 1 is PD, effect. Other than that, the rest is the same. And so we're just inserting that additional level of prediction here for the effect data and using the indicator variable to switch from observation to observation as the routine scrolls down the data set. Remember, the way that this works, it's a recursive subroutine. So NONMEM steps through each record of the data set, making a prediction for that data record. And so it's the value of type on that data record that's going to define what type of prediction we make. The rest of the control stream is the same. You use the same estimation methods. All of that's the same. You just might want to capture the type indicator in your table file so that you can make plotting by PK or PD type. Okay. So next, let's talk about something a little more complicated. Sometimes we have relationships between concentration and response that are not direct. And one of the ways to do that is to model an effect compartment. So here we have a typical compartmental structure for an effect compartment. We have a depot and a central compartment for PK. So compartment 1 and 2 are still your PK model. But effect is not directly related to the central compartment concentration here. And so what we might do is add a peripheral compartment to allow for that kinetic disequilibrium between central compartment time course and the effect time course. And this can represent a number of things. It could be, that there's actual delayed distribution to the effect site, and the instantaneous plasma concentration does not reflect the time course of the effect. It could be that there's some sort of sensitization of the response so that it looks like it doesn't match with the effect relationship. It could be that the transduction of the response takes more time. Maybe there's a cascade of events that has to occur before that response is manifested. There's a variety of different reasons for this. And we can use this empirically, even though this looks like we're just describing a distributional delay. It could be used to describe any one of those reasons. It could also be the result of an active metabolite that happens to be unmeasured, or one that we might not even know about, that might be responsible for the activity, and so therefore shows a delay relative to the parent drug central compartment concentration. Whatever the reason is, there are different ways of modeling this. We can use the multi-compartment analytical advance to do this, and this is probably the most efficient way. So, for example, if we had this model structure, what does this look like? It kind of looks like a PK model with a two-compartment disposition, where we have a depot, a central, and a peripheral, and then a transfer back and forth. The only difference is that this KE0 is exiting the last compartment. Well, we can play tricks with that, so that even though the arrow might be pointing back to the central, we can arrange this so it doesn't impact the PK mass balance, and we could use one of the analytical advans. In this case, it would be advan 4, which is the two-compartment disposition with a first-order absorption. There's some advantages to using analytical advans here, and that's because they're analytically solved. They run faster. It's just an algebraic expression. However, we could use a general linear model or differential equations to do so. And those are described in advans 5 and 7, as well as advans 6, 8, and 9. I have examples of each of these for you in the example set. We'll focus our attention on the analytical advans for this class. Here's a look at the data set. You have ID, time, amount, BV, compartment, and type. Very similar to what we had before. The thing that's different now is this compartment indicator. So when we assumed a direct relationship, meaning that the pharmacodynamic effect followed the same time course as the concentration profile, we didn't need the compartment statement. We didn't need to accommodate any sort of lag between PK and PD. But now we do, and so that's why the compartment indicator is important. So type here is 1 for PK, 0 for PD. Similarly, we have compartments defined as 1, 2, and 3. Let me scroll above here to the picture. Compartment 1 is the depot, 2 is the central, or a PK observation site. 3 is the effect compartment, or where we make PD observations. So when we roll down this data set, you'll see the first record is a dose to compartment 1. The second record is a type 1 PK observation in compartment 2. The next observation at time 2 is a type 0 PD in compartment 3, or at least it's related to compartment 3. Then type 4 and 6, observations at time 4 and 6 are type 1, both PK observations, and then at time 7 we have a PD observation. So you see this structure here just again alternates between PK and PD observations in one DV column. We have a type indicator indicating which type of variable, and then the compartment is also necessary because now, unlike the direct PK PD model, the indirect or effect compartment model has a kinetic disequilibrium or disconnect between the time course of the effect time relationship relative to the concentration time curve. Okay, so that's how you code up the data. Let's look at a model for that. And we'll look at the effect compartment 1 here. So again, this is very similar to our standard setup for a PK model. We have a few comments here. The type is 0 for PK, 1 for PD, and the compartments 1 is gut, 2 is central, and 3 is the effect compartment. So we code our PK model as we typically would. But one thing we're going to do differently here in the subroutine, it just allows this parameterization, is that instead of using one of the clearance volume trans routines, we're going to use trans 1. Remember, trans 1 is the translation routine for PrEP-PP models that uses micro constants only. Okay, K12, K23, K34, that sort of constant. There's a reason for that. We're still going to use Advan4, which is the 2-compartment model with first order input. Let's see how that fits together. So first we have a Ka, that's the first order rate constant from the depot to the central. We have a clearance from the central compartment, and we have a volume for the central compartment. So those first 3 lines are just like you would have for a typical PK model, 1 compartment PK. But then we're defining a Ke0. Ke0 is the first order rate constant defining the time course of the effect time lag relative to the PK time course. K elimination here is clearance divided by volume. Now we have to also identify a rate constant transfer K23. Remember, that's required for Advan4 under trans 1. K23 is the transfer from central compartment to the effect compartment. What we're doing here, and this is really the trick that allows this to work, is that this is equal to the exit rate constant, K, times some very small fraction, so 1/1000th of the exit rate constant. By doing so, what we're doing is making the mass transfer over to the effect compartment essentially negligible. And that's how we can use this analytical solution, this compartmentalized model, to work here. And so wherever we put Ke0, here we're defining it as K32 going back to the central compartment. But since that transfer to the effect compartment is negligible, then the transfer back is also going to be negligible. And then what we do, there's another, well, of course we set the scale for compartment 2 equals the central compartment. We need a scale for compartment 2 because we have observations in compartment 2, and those are PK observations. We also need a scale for compartment 3 because we have observations being driven off of that compartment. And this little equality here just sets up steady state concentrations to be equal Or in other words, the intercompartmental flux is the same. This allows us to view the effect site concentration in terms of units that are similar to the plasma concentration. It's completely hypothetical. We don't have observations of concentration at the effect site, so we're making a prediction at that time. This just scales it to make it a more meaningful set of units. Okay, so the error block is where we're going to specify the PK/PD predictions. Now this gets a little tricky now because we have two different compartments. Now, concentration in the effect site is the amount in compartment 3 divided by the scale for compartment 3. Concentration in the plasma is the amount in compartment 2 divided by the volume. And these are standard terms in NONMEM, A3, A2. You can capture the amount in any compartment by using this nomenclature. This allows us here to capture the amount in the specific compartments and scale it by the volume or scaling factor, and we can derive a concentration prediction. Well, that's handy to have because if we have CE and CP, then we can make predictions of concentration and for the effect site as well as concentration for plasma. We have our usual Emax, EC50, and E0 here. And we can make concentration predictions. Now, because we have a compartment indicator, our value F takes on a different meaning, right? When compartment is equal to 2, F is the prediction in the central compartment. When compartment is equal to 3, F is equal to the concentration prediction in the effect compartment. So F can be used here, although it sometimes is confusing to users. So you might also want to do it this way. I'm just going to type over and write CP here for concentration. And then for the effect model, we use CE. The notation with F is also correct, but it's just sometimes a little confusing because it seems like the same variable is being used for two different things, which it is. It just takes on different values depending upon the compartment indicator. This is a more specific way that it's not going to depend on the compartment indicator. Okay, so we have concentration predictions now and effect predictions, where the concentration prediction is driven off of CP, the second compartment, and the effect prediction is based off of CE, concentration in the third or effect compartment. And then we use the usual indicator variable y equals concentration times 1 minus type plus effect times type. We'll keep using that indicator variable over and over, but the unique thing here is that we're now making predictions based off of different compartments in the model. Okay. Now, there are other ways to model that effect compartment, including differential equations and general linear models. We'll spend more time on that in the next course. But if you're interested, you'll see those in, in eComp2 and eComp3. Those are two different implementations of the same model, just using a different advan routine. There are also mechanisms that we might want to use a non-parametric effect compartment model. This is a case where maybe the PK data are very complicated, messy, and we haven't got time to develop a model, or maybe we haven't been successful in developing the model. And so we'll use the PK/PD data themselves or a linear interpolation of those data to drive the response. So there's not a PK model involved here. That's where the non-parametric, or probably better called semi-parametric approach comes from. And there's an example of that in this control stream. That's kind of a complex topic. I'm going to leave it. I'm including it in this course just for your information, but we'll spend some time in the next course going through that one in detail. Suffice to say that this is quite useful if you have extensive sample data, and that the whole time course has been captured in PK. So it's useful mostly for single dose PK/PD relationships, where the single dose PK is very messy, and developing a PK model is not so simple or straightforward. Before going on, I'm going to pause to answer a question or two. Okay, somebody wants a further explanation on the trick that we use to avoid the mass balance problem. Let's go back to this equation and imagine that this was like a two-compartment PK model where this rate constant returned to the central compartment. If we wanted to describe the kinetics in an effect compartment under this sort of a model, but we don't want to change the kinetics of PK. So there's something quite different from a two-compartment model, which might include just these, I can't really highlight it, but these first two compartments, versus, let me see if I can use this annotation tool. Never mind. A two-compartment model which has these first two components, one compartment model which has the first two compartments, and versus a two-compartment model which has a peripheral compartment. Well, that's not what we're modeling here. Remember, the PK is still a one-compartment disposition. We're just tagging along this peripheral compartment to model a hypothetical effect site. So unless we make the transfer to this peripheral effect site compartment negligible, it's going to start to affect our PK model. And it will treat the PK as if it's a two-compartment disposition, which is not correct. So we do need to make that transfer negligible. Remember, the effect compartment is not representing a true kinetic disposition or distribution to an effect site. We don't have, unless you have measurements of that effect site, you can't really do that. What it is doing is representing a disconnect, a delay in the kinetic time course of effect versus concentration time profile. So I'll look at the code one more time with you. We want this transfer to that peripheral compartment to be negligible. That's why we're multiplying the exit rate constant, K, times some negligible fraction, 1/1000th, and setting that equal to the K23 rate constant. So this is the transfer constant from the central compartment to the effect compartment. We want this to be negligible because we don't want the effect compartment to affect the mass balance for the PK model. And if you were to derive these effect compartment equations, that's the same assumption that you'd need to make. Now, that doesn't mean that we couldn't model an effect in a peripheral compartment if we had a true two-compartment disposition. So imagine that this is really all a PK model with KE0 again returning to compartment 2. So it's really K32. If we had that sort of a structure, we have two-compartment disposition on PK with a first-order input. We could attempt to use the peripheral compartment predicted concentration as the driver for response if there appears to be a kinetic delay. And in fact, that's the first implementation of the effect compartment. John Wagner had looked at LSD kinetics and dynamics and had performed that exact sort of implementation where he used the peripheral compartment predictions from the PK model to drive the response relationship. Subsequently, that was then connected with other pharmacodynamic relationships where there wasn't necessarily a peripheral compartment that would explain the kinetics of response, and maybe there's something else going on to describe that kinetic delay, and that's why we do use the effect compartment. But if you did have a two-compartment PK model, you could always explore the peripheral compartment as a predictor of that response. Let me answer another question here before we move on. If you explain the need of a dummy amount at rho at time 0 for PD variables where baseline is not 0. Initial conditions. Yeah, I'll explain the initial conditions. There's several ways to do that, and I'll get to that when we discuss the indirect response models in just a moment. In this case, we don't have to initialize any of the compartments. What you can do is we estimate an E0 parameter. Go back to the code. You see here in our PK/PD link model, we have an E0 estimated. This is the baseline. And so remember that we're not modeling the response as a kinetic compartment here. We're making a prediction of response based on an observation in the effect compartment. But that prediction could start at a non-zero baseline. And that's what E0 does for us here. This gives us a prediction of the intercept or the non-zero baseline for the response. Now there are other ways when we're actually using the compartment itself to drive the pharmacodynamic response that we have to initialize the compartment to a non-zero baseline. I'll show you how to do that in a minute. One more question. Yeah, so the question is, in the, again, back to this K2-3 relationship, will the PD modeling be highly impacted by the scaling factor? No, it won't at all. This doesn't impact the PK or PD. In fact, if you look down here, as when we're setting the scale for that peripheral compartment, we're using K2-3 as one of the factors. So all this does is it puts the effect site concentration in terms of the plasma concentrations. So try it out. This is a very straightforward approach. It's been used over and over again, and it's consistent with the assumptions you need to make for an effect compartment. Okay, moving on. Talk a little bit about a model that has been published to describe tolerance to response. And this is pharmacodynamic tolerance, such that concentration leads to a particular response level initially, but then later that same concentration leads to a diminished response. So there's some tolerance, and this is often viewed as a clockwise hysteresis loop between concentration and effect. But the way that we can imagine this is that the response is driven from the central compartment. So we have a depot and a central compartment model. Just pay attention to these first two compartments. That's our PK system. PD is directly related to central. But there's some other effect going on here that's a first order process given the concentration in the central compartment that initiates a tolerance, a feedback of some sort. And so this is an empirical way to model tolerance, where you allow that tolerance to build up, and then the tolerance comes back into the response model or the pharmacodynamic model and diminishes the effect. This was used to describe the effect of nicotine on heart rate back in a classic paper. You could see the code here is in a file called tall PKPD. Let's take a look at that. So the same sort of thing here. We're going to have the sequential observations, PKPD. We're going to have a 3-compartment analytical system here, or actually first order plus 2-compartment disposition, again with trans 1 parameterization. But now we have 1 is the gut compartment, 2 is our central and effect. They're both observed from the central compartment. And 3 is to show the buildup of tolerance. It's going to be quite similar to the effect compartment model, where we define the PK parameters, except now instead of a KE0, we have a K-tall, which again does the same thing as KE0, except right now we're defining the time course of the tolerance development. We use the same implementations here to, again, view this as a hypothetical tolerance compartment. It's not affecting the mass balance, so we have that negligible transfer. All the same stuff as we've done with the effect compartment. The real difference comes down in the error block, where we define the model prediction. We define C-tall and CP. C-tall is the compartment, C3 concentration, or in other words, A3 divided by S3. CP is compartment 2 concentration, A2 divided by V2. We define in the model parameters, this one here was a linear model with a slope and an EC slope, but then the tolerance enters using this EC tall parameter. That's sort of the sensitivity, or the EC50 of the tolerance effect, and then a baseline effect E0. We then can relate effect by defining our model E0 plus slope times concentration, and that's your simple linear pharmacodynamic model right there. But then we divide that by 1 plus the concentration in the tolerance compartment divided by the EC tall parameter. So as you see, what happens here as the concentration in tolerance increases, the response is blunted, right? The denominator here is getting larger, and so the response is diminished, even though CP might be the same. Similarly, if EC tall is very small, a very potent tolerance effect, there's going to be more of an impact of the tolerance effect. If EC tall is high, there'll be less of an impact of the tolerance effect. Okay, but the critical thing that's taking place here is that in the prediction for one effect here, we have two different concentrations playing a role. We have CP, which is from the second compartment, and we have C tall, which is from the third compartment. So that's the tricky part. Here we have, this is how we can combine concentrations from two different compartments to create a single prediction for effect. And then the PK, the concentration observation, is the same as always. It's a, in this case here, an exponential residual model based off of the central compartment. And we use our indicator variable again to switch from concentration to effect predictions. This is very similar to the effect compartment model. The key being is that now we have an effect prediction that's based off of two different compartment concentrations. You could imagine using a similar approach if you had a parent and metabolite model and you wanted to allow both parent and metabolite predictions to impact the response. You could use a similar type strategy where we are using concentrations from both endpoints. Okay, so that's the tolerance implementation. Now we'll get to something that's a little more complicated and will require us to use the differential equation models in Advan, and that's the indirect pharmacodynamic response models. For these models, response is modeled as a continuous function of time with a differential equation. So it's not like the direct or indirect PK/PD models where response was modeled as an algebraic expression, right? An Emax model maybe with an E0, or an Emax model with a tolerance effect, something like that. This is not what we're doing now. Now response is actually a compartment in the model. It's not an algebraic expression, it's a differential equation. And we can mediate then the drug effect by inhibition or stimulation of the response formation or offset. And so the PD effect is on the rate constants here, or zero order rates, and not directly on the response itself. That's why it's called an indirect pharmacodynamic response. Okay, so let's consider this now. The easiest way to think about this is starting at baseline. So before you've added any drug, there's some response over time, and we'll consider this response according to this graphic, where that response is constant over time. It's essentially a non-changing steady state value. So the change in response over time, drdt, is 0. It's at steady state. If we view this response then as a compartmental model where the compartment amount is actually the response itself, that's being driven by some zero order input, some constant input rate, and an offset that's first order, k out. We then can write this differential equation as k in minus k out times response. So the zero order rate minus the first order rate constant times the response value. So we could solve for response here at baseline, or R0, and that simply becomes k in divided by k out, the ratio of these two. So given that derivation, it gives us a strategy for how we can model this initial condition in NONMEM. Since we say that the response at time 0, or R0, is equal to the ratio of k in and k out, we could initialize that compartment by initializing the amount in the response compartment. And so this is one way to set initial conditions, is we set a data record to initialize the amount using a unit dose, a dose of 1. And then we estimate the baseline value using the bioavailability parameter, F3. How can we do that? Well, because remember, when we add a dose, the bioavailability parameter is always estimated as some number, some fraction times that dose. So if we put a dose of 1, then bioavailability becomes the estimated parameter that's necessary to scale that unit value of 1 up to a baseline. So if, let's say, our baseline observation was 100 units, then our dose was 1, then F for that compartment, as let's say it's compartment 3, F3 would have to be equal to 100. 100 times 1 gives you a baseline observation of 100 units. And so here's how we would parameterize that. We could say that K in is estimated and K out are estimated, and you know, we might try to estimate fixed and random effects on both, although that might be difficult. And we simply say that R0, or in other words F3 here, is equal to the ratio. This is the response times 0. And then, you know, you can change this around. You can try to estimate K in and R0, or K out and R0, or K in and K out, but we can't estimate all three. So we estimate 2 of the 3 variables here to set the baseline conditions. So let's look at the data set there as a first step. So remember, we're using the data to introduce a baseline value or an initial condition. And recall that we have PK/PD model, so we have a type indicator. Here, I believe we have a type 0 is PK, type 1 is PD, type 0 PK, type 1 PD, and so on. We have a compartment indicator. Type compartment 1 is your depot. Compartment 3 is the response compartment, and compartment 2 is the concentration compartment. We initialize PK with the first record by putting a dose in, and the dose is initialized into compartment 1, a dose of 500. Okay, that's fine. That's how we always initialize PK, is through a dose. But now we have to initialize a baseline value in one of the differential equation compartments for response. And the way we do that is we initialize a value of 1, which will be scaled by F, remember, into compartment 3, which is our response compartment. So this is a dummy data record. You see it's also at time 0. It's the starting time point. We're initializing that compartment by using a data record. Now, NONMEM 6 and 7 have allowed a new feature here where we can actually specify the initial conditions right in the control stream. So for example, amount 1 underscore 0, A10 equals some value, and we could do it that way. But this is a classic method, and it works across NONMEM versions. So you might want to be familiar with this. But that's the basic idea. We set up the initial conditions such that the baseline amount is to be estimated given the observed baseline, and then some parameters here for the onset and offset of the response. Okay. So let's look at the implementation now when we start to add the drug effect. Now there's a variety of versions of this model, all different types of assumptions about where the drug action is. We'll review 4 of the more common ones and how they're implemented. So first we could take the baseline conditions, K in, K out, and response, and we can perturb them now with a drug effect. This drug effect has a negative impact on K in, or an inhibitory effect on K in. So what we can do then is write the differential equation such that K in is being modulated now by this inhibitory Emax, 1 minus Emax times C, divided by IC50 plus C, minus K out times R. So this is inhibitory Emax, and we've got to constrain Emax to be contained between 0 and 1 because you can't have more than 100% inhibition. But the net effect here is that we see a drop in the response over time. As the drug disappears, then the response returns to baseline. So that's inhibition of K in. We can also modulate the system here to inhibit K out. So just like we had the inhibition before on K in, now we have the inhibition modulating K out. An inhibitory Emax model here is used, and the Emax parameter again is constrained between 0 and 1 because we can't have more than 100% inhibition. And by inhibiting K out, this causes the response to increase over time. You can think of this more physiologically, and sometimes the model is only selected based on empirical goodness of fit, but you can think of this one, for example, as inhibition of an enzyme which catalyzes the removal of something. For example, think of acetylcholinesterase inhibitors. Acetylcholinesterase is the K-out mechanism here for acetylcholine, which has multiple pharmacologic responses. A cholinesterase inhibitor will come in here and inhibit or block this output and will increase the response over time. So you can view these complex interactions in terms of their pharmacology and try to select the best model based on that mechanism. Similarly, we can modulate through stimulation here of K in. Stimulation of K in allows us to increase the response through upregulating K in. You see that response increase over time until a drug is washed out. And I actually have a typo here. I apologize for this. This should be a 1 plus, or this is a stimulatory Emax model. And in addition, we can stimulate the K out. Again, another typo here. This should not be a negative. This should be a positive effect. I'll fix these slides and repost. But the K out is now stimulated, and so by stimulating K out, you're diminishing the response more rapidly because of the drug, and you see the response drop over time. So you'll notice that stimulation of K out and inhibition of K in have the same sort of shape, whereas inhibition of K out increases response over time, and so does stimulation of K in. So there are complementary type models here, and sometimes they're not. They are different parameterizations because one is happening on a 0 order, and the other is happening on a first order rate constant. But they're often difficult to empirically distinguish when developing the model. And so, like I said before, lots of times the choice of this model is based on a mechanistic understanding or an assumption of a mechanistic understanding rather than just an empirical goodness of fit. Okay. All right. I'm going to answer a couple of questions and then we'll look at the code. Okay, on the data set that I presented before, I had a type 99, and that was really just an indicator. I used type 99 because I wanted to separate the dosing records from the observation records in the type column. And so type 99 reflects all of the initialization doses for the response compartment, as well as the doses into the PK model. Type 0 and 1 are PK and PD observations. You could use, really could use any value for the dosing records. The type is not, dosing records are not used when it comes down to the model prediction. Remember, it's just the type indicator on the particular observation record that's used to set the prediction type. I just use that to help us separate those records for plotting purposes later. Remember, type is not a NONMEM understood variable. It's user defined. And so you could call it whatever you want, and you could use whatever numbers you like. I think it's useful to use the 0-1 binary data, but you could use type in any way you'd like. Okay, let's look at the code for those models. And we have indirect 1 here. So as far as the PK model goes, we're going to do something a little different now. We're going to specify differential equation advans. That's what advan 6 is. This is a general differential equation model. Trans is always 1 for these. We work in microconstants. We can back calculate clearances and volumes. And there's a new piece that we need to identify here. Tall equals 3. Tall is an indicator of the tolerance for the numerical integration precision. The higher the tolerance we specify here, the smaller the step size for the numerical integration. So recall what we're doing now. When we go to differential equations, it's no longer an algebraic solution. We now have to do a numerical integration of a concentration time or response time relationship. So it's a dAdt. Change in amount versus time. We have to numerically integrate that, and we use numerical integration algorithms that are included in NONMEM software to do that. Advan 6 uses something like the Runge-Kutta method. Advan 8 uses Geer's method. And then there's new Advan 13 in NONMEM 7, which uses the LSODA, which is a very intelligent and robust differential equation solver. But what we're doing is we're integrating that. And the way we integrate that is we take very small steps in time under that time course. The tolerance value here, the higher the tolerance value, the smaller the step size, or the more accurate the integration will be. We can start at a value of 3 possibly. You might want to bump it up a bit depending upon how many significant digits we're trying to obtain in the final estimates. We also have to introduce this other subroutine called model, which defines the compartments of the model. Remember, this is not a predefined model. It's a very general model. So NONMEM has no idea of knowing how many compartments we have. So we name them here: compartment, gut, concentration, and response. That identifies that we have 3 compartments, and they have names. You can specify other terms here for the compartments, whether the default for dosing or default for observations, all that sort of stuff. Check the help files on $model, and you'll see all of the options there. So we define a PK block the same as always, where we define PK model parameters, their fixed effects and random effects. That's the same as always. I'm also going to define here the K in and K out. Remember, we've used those to define the 0 order rate of formation for the response parameter and the first order exit for the response. And F3, which is our bioavailability for compartment 3. Or in other words, here it's our scaling factor for that dummy dose of 1, which is equal to our baseline response. And the baseline response is just equal to the ratio of K in and K out. We've already derived that. We can define Emax and IC50 here as well. So there's a new block we're going to introduce here, DES, $DES. This is the differential equation solver. And in here we can define models in terms of differential equations. So here we'll define concentration in compartment 2. That's just A2 divided by V2. We're using the same notation as we had in the error block before. And we can define effect now. Effect equals Emax times the central compartment concentration divided by IC50 plus this central compartment concentration. Now let's specify the differential equation. So we're going to have compartment 1, which is going to be the depot. So it's minus Ka times A1, right? Compartment 2 is a central pK, so it's going to take what's coming in from the depot, Ka times A1, minus what's leaving the system, the elimination rate constant times A2. And then dA dt3, this represents the kinetics of the response compartment. Okay, so this is our indirect response. So remember, it's an inhibitory response. We had K in minus K out times R, right? But now we have an inhibitory drug effect. So it's K in times 1 minus E, or 1 minus this Emax relationship. That's going to be our inhibitory Emax on K in. K out times R, in this case R is A3. That's the inhibitory Emax model on K in. When you get down to the error block, it's the same as always. Cp is equal to the amount in the central compartment divided by volume, and so our concentration here is just equal to Cp times some exponential residual error. When we get to effect, though, effect now is not an algebraic expression anymore. Effect is just equal to the amount in the differential equation compartment. So effect is equal to A3 plus some residual error. So our prediction for response now is actually what's contained in the compartment. We don't have to enter that into a pharmacodynamic model. We need to make it part of an Emax relationship because the Emax effect is happening indirectly on K in here. And then using indicator variables, as always, we switch between concentration and effect. But this is different than the other PKPD models in that the response is not directly related to concentration. It's indirectly related in that the drug effect is modulating one of the components of the response input or output. And then our effect is just simply the amount in that compartment. Otherwise, it's all the same. We use indicator variables. We have 2 different residual errors, and so on. When you're setting the initial estimates for the theta here for Emax, Emax here we set as theta 6. You might want to, well, in this case here I fixed it at 1, which might be a reasonable assumption if you think that the drug can 100% inhibit the K in. Or if not, you at least need to bound it so that it becomes no greater than 1. Let me look at if there are any questions at this point. Okay, this is a question about the definition of the baseline. Why we can only estimate 2 out of the 3 parameters. If we go back to that derivation, we said that F3 is equal to R0. F3 is the baseline concentration. If we believe that F3 is the baseline concentration, we also derived the relationship of the formation and exit rate constants for that. And maybe I'll go back to the equation to show you that in more detail. Right here. R0 here is the same thing as F3 in our model. It's equal to K in and K out, right? Because when the response over time changes 0 when you're at baseline. This relationship holds. Well, we have an observation for baseline. And what we want to do is estimate the parameters that govern this model. Well, it's not an not all three of these parameters are identifiable. In fact, there's an infinite number of combinations of these three. But what we can do is say that we're going to estimate R0, or predict R0 by estimating K in and K out. Or alternatively, we could predict K out by estimating R0 and K in, or we could predict K in by estimating R0 and K out. But you can't estimate all three because of the relationship here. Okay, one is a predicted value that's going to then be compared to the baseline. So hopefully that explains the relationship between those three parameters. Somebody also asked a question about type 2. That was just another indicator to capture something for plotting. It's not important. Okay, let's look at code from another one of these. Let's look at number 2 here. This is the indirect response model where we're inhibiting K out. So now instead of stimulating K in, we're going to inhibit K out. Instead of inhibiting K in, we're going to inhibit K out. Excuse me. The model structure is all the same. We initialize the compartments the same. We can also initialize by using the F3 parameter. In a differential equation block, we specify concentration compartment 2, our inhibitory Emax model. And all the equations are the same, except now we've moved this inhibitory Emax relationship from the K inside to the K out. Now we're inhibiting K out. Again, Emax needs to be capped here. We're fixing it at 1. It's going to be at least constrained to be no larger than 1. And then I bet you can imagine, how do you do this same thing for the stimulation models? Well, it's very similar. Here we're going to stimulate K in, and so Emax is being used to modulate K in, and we don't have to write this in a proportional sense here. We can just multiply by E. As long as E is greater than 1 here, you're going to stimulate K in. And so that's another way to model this, stimulating K in. If we're stimulating K out, we would just move the E to the right-hand side here, next to K out. Okay. So those are the general structures for what we call the indirect pharmacodynamic response model. What I've described today probably covers 95% of the pharmacodynamic models that you'll deal with. There are some more advanced topics, including cell growth models, models for cell lifespans that are necessary to incorporate, models for precursor pools, and other types of feedback and tolerance models. And we get into some of these in the next class, MI212. But this will cover 90 to 95% of what you need to do from pharmacodynamic modeling. I'm going to point out one other thing. I'm going to pull up the SIMI interface. Just to look at the to illustrate the other way to initialize compartments. There's something here called the compartment initialization block, or compartment initialization A0. Either one of these will help you to do that. Yeah, let's use this one here, compartment initialization. So we can define here a value for A0 for a particular compartment. A0 means the amount at time 0, or the amount at baseline. for compartment N. N would be 1, 2, 3, 4, whichever compartment. And we can just set that equal to something. Okay? So in our prior model, I showed you the way that's consistent across all NONMEM versions. But if you're using NONMEM 6 or 7, you can use this A initial parameterization. And we could change it. Let's look at this one here. Instead of using the data set, we can just write the model like this. A0 underscore 3 is equal to Kn divided by K out. It takes the place of the F3. And it also takes the place of having to use a data set to initialize that value. Okay, so I'm going to comment this one out here. But this is another way to initialize baseline. It does not require dummy data. That only works with NONMEM 6 and 7. If you're using NONMEM 5 or earlier, that won't work. And plus, this general approach that I've described using the dummy data record is also consistent with other software methods that don't have this this initialized variable like A0. Okay, so that wraps up the PKPD section. All of these models that I've included in the examples actually do run, and you have data sets for each one of them. And I'd encourage you to try those on CIMI. There's no official homework problem, but you might as well take advantage of having access to this and run them if you'd like. The data sets are all included in the examples folder that I've posted on the course site. And so you could try to run these or use them, you know, if they fit your project for the class or some other application. That's fine too. I'll pause for a minute to see if there's any final questions for today's topic. As I promised, the lectures from this week are not going to be included in the final exam. There may be one question from last week's lecture on the advanced methods, but the bulk of the questions on the exam will be from the prior lectures. Those questions in the exam will be posted this week, as I mentioned before. We do have one more lecture which we'll do in our Friday session this week. That's a short one. That's just some discussion about best practices and regulatory guidance related to population PK work. Okay, any additional questions? I guess we'll break for today then, and if anything follows up afterwards, please feel free to communicate via the discussion site. That will be open throughout the rest of the course, all the way up to the end of July. So if you have additional questions, if you're catching up on lectures, listening to the recordings, you can always ask the questions there. Thank you for your attention, and we'll talk again on Friday. Bye for now.